no, about the turbo codes today. If you had a look already at the lecture slides, you noticed it's also quite a complicated topic, but we will just get an overview today how this is working. So if you understood the trellis diagram, what you already see here on my board, you can also understand how the turbo codes are working without going too much into detail. So when I come up with the lecture slides, usually my goal is to provide such a level of detail that you will be able to implement stuff if you have to. This is why you will find quite many equations on the lecture slides. So not only being able to implement stuff, but also being able to understand where typical equations come from that you will find if you consider implementing a turbo code. Okay, one more student, good morning. Okay, but before we do this, we start again by looking at what we did last time. So we talked again about the Viterbi decoding. I think this is clear now how this works, no? So we don't have to explain this once more. And after that, we basically came to the recursive codes that are used in UMTS, like in 4G wireless systems, and they are typically in turbo codes. So we will see today for the turbo codes of UMTS, we will have two concatenated recursive convolutional codes, similar to the one that we've used here in our example. And as compared to the regular convolutional codes, those are a little bit more difficult to treat because you notice we have the feedback here, feedback path in the drift register, which makes things a little bit more difficult, but it makes the code also, let's say, more powerful. More powerful, again, in terms of redistance. Okay. There. Sure if I missed to save some slides last time, but check. Okay. So this is actually where we want to continue today, looking at the turbo codes. More specific. We have a look on parallel, concatenated, convolutional codes, PCCC. Used in TS. Say, for example. And the convolutional codes that are used are recursive convolutional codes. Let us have a look. Structure. So the UMTS. Turbo encoder. Let's look at the encoder first. That's the more easy part. So again, we start with a sequence of bits. And those bits also include the termination. So we also have the termination here. I spoke about the termination last time, we need to switch basically the feedback to the input of the register, and this will make the input of our memory stages always to be 0. So in this way we can reach the all 0 state at the end. So our UMTS encoder has a memory of 3. So we have 3 delays here. And TB denoting a delay of like 1 bit duration. Okay, and then again, the encoder is defined by generators. So we've learned we need a feed forward, feedback generator to define so which path go back in the feedback, which path go forward towards the output. So for our UMTS encoders, we have a feed forward generator, G-feed being 15 octal. Actually, this is not a vector yet. I just want to make it to a vector. So let's not underline this G here, G-feed. And in order to convert this to binary, to determine our feedbacks, just do this, convert the octal binary. So the 5 is 4 plus 1. So this would be the binary representation. So G feed forward. Because we can skip the trailing zeros, this would just introduce 2 more delays without the outputs being used. So there's no use of these trailing zeros. Just need to be careful if we have several generators. Of course, the length of the register would be determined by the longest generator. So, but here, both generators will be of length 4. So this will be generator like this. So we get the feed forward path by using first one here, using the second one here, not using the next one here, and using the last one. This is basically how our feed forward generator looks like. This will produce our second output. I will come to the first output right away, AR2. And we need a feedback generator. This one is 13 in octal for our UMTS encoder. Just like equivalent, worded the same way. It's 1 from the 1, and 3 will be 0, 1, 1 in binary. So the first one in the feedback generator denotes to this guy. So we will always need a 1 here. Then we don't use the second one, 0 here. We use the third one, this one. And we use the last one, this one. So this defines our feedback. So I can also use some color. Maybe this helps you remembering how these guys were defined. So this is our feed forward generator using first, second, forth. Back generator here, the guys using first, you will always have the one here, the third and fourth. This is basically how it's just one question here. So here was a question related to how to read the generator. So we start basically from the left to the right. So meaning the first one belongs here to the first connection and so on. Okay, so we use a recursive systematic code. Oh, wait, let's complete the termination. Yes. Didn't get the last point. Got it correctly. So here we had a question about the generator and how to convert them, if I understood it correctly. So of course, in the octal number space, you can only have like numbers here going like from 0 to 7. And you need to convert this. For example, if you have like the 135 generator, this would be 0, 0, 1, 0, 1, 1, 1, 0, 1. So this would be already a quite larger memory. So this is typically how you convert octal numbers to binary numbers. You always need to, or if you want to do it the other way, if you want to go from binary to octal, you would have to form groups of 3-bit, because if you calculate then basically the weight, you will have here like the 1, 2, 4. So the maximum number would be 7. So this would give you values from 0 to 7. So you need groups of 3 bits to convert from binary to octal, and also the other way around. If you convert from octal to binary, take the single digits, which can be between 0 and 7, and convert them to these 3-bit words. Probably you are more familiar like with the hexadecimal notation. So often students learn this somehow, where you have was from 0 to F, I think. Yes. So here we have a question from Kazan. So if the feedback generator is 0, then the feedback will be after the first memory. Ah, okay. So here we have a question. What if you don't have to write this, I will erase it right away. What if the feedback generator starts with 0? So actually you will not find codes where the feedback generator starts with 0, because you always have the 1 here at the beginning, which denotes that we have a feedback at all. For all coding schemes, you will find the feedback generator must start with a 1. So you just cannot have the feedback generator starting with 0. Okay. So let's complete this guy here. We also want to have the termination. So we already studied yesterday that we can get this by shifting the input to the feedback. And I already said we have a recursive systematic code. So this means one of the outputs will be directly the same as the input. This goes. Yeah. So our first output is just the same as the input. Actually, wait, I made a mistake. So we would use the guy here after our termination switch, because otherwise if we switch to termination, we would not get any output bits AR1. We need to go here, systematic. Okay, and then we basically have the same structure again, but with interleaved bits. So we will talk about the interleaver right away. Interleaver. In block diagrams, you will also sometimes find there like a capital pi, which is often used for like permutation matrices. So this is somehow a permutation of bits, which we will see. And then basically this enters the same structure again. Let's do it this way. Also here we have the termination switch. We have feedback. We can do this a little bit faster here. Basically the same. And we have here the addition and the output, giving us the second output here, AR. Same as above. There's two identical encoders. Let's draw a box around it. So two identical encoders are used. So one, this is the interleaved sequence of bits. We will see why this is important. This is the interleaved sequence of bits. So again, this is actually the structure that you will find if you look in the standard where UMTS physical layer is defined. So you will find a block diagram pretty similar to this one. Okay, but now let's have a look at the interleaver, because this is an important part here also for the understanding. Just give me a hint if this was too fast, so I will go back. So What is an interleaver? And why is it used here? Yes, so let's come to one reason why typically an interleaver is used. Typical usage. So imagine we want to transmit a couple of bits, saying here from A1 up to, it's really something, A2, B. Let's say here up A9. Transmit. And we receive or we decode, let's say here, A hat. So, and now we assume that an error occurred. A couple of errors occur. About wireless applications, there's one typical pattern of like errors, like so-called burst errors, where really a couple of bits in a row get corrupted. For example, if you have like a fading, like destructive interference of your received power will go down and 10 bits will be lost, for example. So it's typical to have like this burst type of error patterns. Burst error. Couple of bits wrong. In each other. And now just think back to our Viterbi decoder. So the Viterbi decoder will face a problem if a couple of bits in a row are wrong, because then it would fail to find the optimum sequence. So this is difficult for decoders. Decoders can deal better single errors. Again, imagine our Viterbi decoding. If just one bit is wrong out of 3, my Viterbi decoder will find the correct. So therefore, what is typically done to combat this burst type errors is the use of an interleaver. So let's see what this does. Most simple interleaver. so-called block interleaver. So for such a block interleaver, we could simply write in our data like in rows of a matrix and read out the data in columns. So we just basically mix up the order. So this means we write here A1, B, A4, A5, 6, A7, 8, A9. Twice. And we read column-wise. So the resulting sequence would be A1, A4, A7, A2, A5, A8, and A3, A6, A9. And again, we would transmit this. A1 hat, A3, wait. A4 hat, A7 hat, so on. And we assume again, exactly as in the first case, like this 3 bits should be corrupted by our burst error. But of course, what would follow here is like the de-interleaving. Again, use this block interleaver, write the data in, read out to get the order as we had it before. So this means at the end, we would get here A1, A2 hat, A3, A4, A6, A7, with A4 being corrupted by error, A7, and A2. So I notice here, this was the goal of our interleaver. The burst error is split up. Burst error is distributed decoder be able to correct. The errors. So this is the typical application of an interleaver to reorder the bits in order to split up this burst type of errors that occur in wireless communication. Or just imagine you just receive data and next to you somebody just turns on his mobile phone, which does some signaling with the base station, so you might get some interference from the neighboring mobile. So this might also cause this kind of burst type errors. And well, of course, in practical system, larger interleavers are used. So maybe like 1000 bits get interleaved. And you really split up these errors nicely over the whole sequence, and your decoder will do a good job in correcting these errors. So this is the very basic field of application for the interleavers. But here the reason is slightly different. Let's underline this. This was the typical usage. And now we will see why the interleaver is used in our turbo encoder. Purpose. Turbo encoder. So again, imagine we have bits that we would like to encode, call them U. Take again 9, so we will use a block interleaver. 6, U7, 8, U9. And again, we do some block interleaving. Let's write just general, some interleave. So because typically also in UMTS, I think pseudo-random interleavers are used, where you just basically come up with a random sequence that also the receiver knows how to rearrange your bits. So we just use the block interleaver for simplicity. So interleaving. Let's say, for example, block interleaving. Let's just write the indices, just do not mix it up with the bits. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So, and if we read this out column-wise, we get U1, U4, 7, so the same as before. 2, if 8, U3, U6, and U9. And those are the sequences now to be encoded. Now it's important to think back about our convolutional encoder structure, so this shift register structure, so we know our current output will be influenced by the previous bits. So depending on the memory, 2, 3 previous bits, or if you have the recursive code, maybe even more previous bits. But just look at the example. If we look now, let's take bit 5. It will be encoded using also like linear combinations with the previous bits. So U5. Be encoded such that the output also contains information about, so the ones that are linked to my current output, in this case, U6 and U7. Or also 8, 9, depending on the memory of our code. So 8, depending the memory. And if we look at our interleaved sequence, notice here U5 will be encoded using U8 and U3, different neighboring bits here. 5 will, or the output that we get from encoding U5 will contain information on U8 and U3. Let's write it similar as up here, be more precise. So the output for encoding 5 will contain information U3, and so on. So this means we link different bits together in these two encoders. This is why, as we look at the decoder at the end, we will see that we can get some independent information from decoding UR5, which has been encoded by a second encoder, independent information as compared to U5 having been encoded in the first encoder, because here U6 and U7 contributed to our output, and here U3 and U8 contributed. So we have two statistically independent encoded versions of the same bit. So this is the point of using the interleaver here. And you already see basically what could be bad about this interleaver. So for example, if we had a memory in our encoders of like 9. So this means in any case, we would use the 9 following bits. So basically all possible bits would occur or would contribute to the encoder output 1. And also here, even if we interleave the 9 bits, if we have a memory length of 9, also all bits would contribute to that. So this is why we need actually large interleavers. We want to have this sequence as statistically independent as it can get, using large pseudo-random interleavers to make sure that our bits down here have different neighboring bits as up here. So let's say here the goal get statistically independent encoded versions of the same bit. It will become more clear even as we look at the decoder, because then we will see the benefit actually of having these encoders. Okay, this is actually also already next looking at decoder. Unless there are questions related to this interleaving. Okay. Let's look at the decoder and it will become more clear. Turbo decoder. So for the turbo decoder, we will basically use decoders in like a recursive way. Use actually map decoder, maximum a priori probability decoders. We will not go into detail there. So let's just say here decoder 1. And we use another decoder. So the first decoder will get the systematic bit, so the noisy observation of the systematic bit. So actually in my lecture slides, I call this AR1 prime. See observation of systematic bit. This goes in here. And what also goes in here, the AR2 prime. So basically the observation of our first encoded bit. See observation. From bits being encoded by encoder 1. Okay, and with this, basically, my map decoder can already come up with an estimate for the bit UR. So if we think at time step R, we want to estimate bit UR from this noisy observation of the systematic bit and from the encoded bit. By processing the trellis, it will come up with the log likelihood ratio if bit UR is more like a +1 or more like a -1. So this will come up with some estimate. So here we get some extrinsic information.
Sir, what is the systematic bit here? It is not clear. Means you have written noisy observations of the systematic bit.
Okay, yes. So maybe let me show you a slide related to this question. This is what I do typically go into more detail there. Just look at this slide. So this is basically how I use the variables here. If I explain the turbo codes, we want to transmit the information bits U1 up to UN. We have this rate 1/3 encoder, which will produce the systematic bit being just the same as UR, and the 2 encoded bit encoded from encoder 1 bit encoded from encoder 2. So, and those mapped to ±1 or ± square root EC, those are the values that are transmitted using, again, an additive wide Gaussian noise channel. And those are the received values then. So for bit UR, we receive, again, 3 values. The noisy received bits, where the first one is just the noisy received systematic bit. Later in the lecture slides on the derivation, I will call this YR, just noisy bit. So no encoding included here, seeing UR goes directly in here, is received here and mapped again in this vector of values Y. Let's look again at the encoder. See here the same thing. So notice there's basically nothing happening with this first systematic bit. It's just if we transmit bits here, UR +1, so on, those bits are directly mapped to the output. So as we know this from the systematic block codes, like the information bits are directly part of the code word, or here, the information bits are directly a part of the encoded sequence.
So, sir, the bits which are not being interleaved, they will be called those systematic bits.
So the systematic bits actually result from the non-interleaved sequence.
Okay.
Yes.
Okay.
Maybe, yes, this could also have been your question. So why do we have no systematic bit here in the second branch? We only need the systematic bit once. We will use this in both decoders, as we will see right away, because if I de-interleave like this sequence, I get the same order as I need it down here. So I just need the systematic bits only once, but one time in the interleaved sequence and one time in the non-interleaved sequence. Okay, let's see. Extrinsic info like estimates. Or log likelihood ratios. So it depends a bit how far we get today, if I can actually tell you how this decoder extracts its information from processing the trellis diagram and using here the noisy observation. So for now, we do not know how this works, but just assume from observing these values, these sequences, this decoder can come up with some estimates. Okay. And we want to use this information for our second decoder, which actually processes the second, or the bits being encoded by the second encoder, so the AR3 prime. So here, second encoder. But now we actually need to consider your point that you were asking. Here we process the bits in the interleaved order. So AR3, this is basically resulting from the interleaved sequence. So this means if we want to decode this also by using the information we get from our noisy observation, we also need to interleave our noisy observations. This is why we need to make the order match. AR1 prime. So also here we use it's down here, AR1 Also here we use the noisy observations, but we need to make sure that we use the sequence in the correct order. But now I want to use in decoder 2 what I already know from decoder 1. I want to use this information that we figured out on the bit to be estimated, want to use it here. But notice here on the left-hand side, we have the non-interleaved version. Here we process the interleaved version. So if I want to make this a line, I need to interleave my results here. Leaving to make the order match. And then my decoder 2 can use this information. So this one gets it as a priori information. Just to give you already a rough example how this could work. So decoder 1 is starting, looking at our noisy observation and processing the trellis diagram from our encoder 1, and it comes up with an estimate. For example, bit UR is like with 60% probability of 1. This information is fed back or fed forward to decoder 2. Decoder 2 has now already more information. Decoder 2 also looks at the noisy observation. It looks at the trellis diagram, like from encoder 2, so it processes the trellis diagram, comes also up with an estimate for bit UR, but additionally, it can use the estimate from before, from decoder 1. So decoder 2 has the noisy observation, it has the trellis from the encoded diagram, from the encoded bit, and it has the a priori information from decoder 1. So here we already have some more information to decode bit UR. So maybe at the output of decoder 2, we would get bit UR as like with 80% probability of 1. So we would get a better estimate as we have some a priori information already. And this will be fed forward again to decoder 1. Notice again on the right side, we processed like the interleaved sequence. So this means if we want to feed this back to decoder 1, we need to de-interleave sequence here again to make the order match. Denoting this here. It's this like de-interleave. And then maybe we know with 80% probability UR is a 1, feeding this back to decoder 1. And then decoder 1 would start again to decode its bit, but now with some additional a priori information. So decoder 1 will now again look at the noisy observation, it will process the trellis, and it will now use the fact that it knows from decoder 2, like with 80% probability, the bit that I want to decode is a 1. It has more information now, it will decode again, maybe it will come up like with 90% probability it's a 1, feed this back forward to decoder 2. Decoder 2 will start decoding again, and in this way we basically improve our estimate from iteration to iteration as we gain more and more information. This is the whole idea. So let's write here, decoder 2 generates independent information on the bit to be estimated and this will be used as a priori information for decoder and so on. There's one typical questions that students ask here. Maybe also my block diagram is not so nice. So now the question could be, how do we get the estimates at the end? Right now, this is a circular information going around here, but where's the output of this thing? So at a certain point, we just would use after well, you have different methods there. You could say you have a fixed number of iterations there. Like you would say after 3 iterations, you stop the loop, or after 5 iterations, you stop iterating. Or if you would do it more smart, you would basically watch the increase in information. So you would stop doing recursions in here if the information doesn't increase significantly anymore. This could be 2 methods how to stop this thing, either having a fixed number of iterations or iterating as long as you get significant increase in information. So let's just use the more simple one. After, let's say, n iterations, output, and if we had a closer look on this algorithm, we will see that we will have here again a vector containing log likelihood ratios like minus 3.5, 4.1, 1.4, and so on. LLRs, and the sign of L would be then basically -1, 1, 1, and mapped to bits you had. -1, map it to the 1 bit, the 1 we map it to the 0 bit. So this is basically how we would get the result at the end of what's method. So again, it's important for you to get the main point, understand why we have these 2 encoders, why we have the interleaver. Main purpose is to generate independent information. Only in this way we can improve the estimate here from. If we would use the same information on the left and on the right side, there would be no way how to increase the information. Or maybe speaking a bit more in terms of entropy, increasing the information, we could also say reducing the uncertainty. It's the other way to explain. So let me show you some typical here. So here I have a simulation result coming here from a reference. So it's somehow difficult to find examples that are not too difficult, but still give you some insight on what is going on. In this publication by these French guys, or also Japanese, obviously, we have an example of the performance of these turbo codes. Let's have a closer look at this one. So actually, they simulated a turbo code with rate 1/2, but actually you see we have also 3 output bits. How comes they only have a rate of 1/2? So if you have 3 output bits for each input bit, we would get a rate 1/3. But notice they do some so-called puncturing. So this means they only transmit every second of the encoded bits. So the circles are the bits to be transmitted. The X's are the bits that are not even transmitted. So in this puncturing, this is typically used to adjust the rate of your codes. So for example, if you have a strong code like this, it's not even required to transmit all the bits, because we know our codes are very powerful. If one bit is missing or wrong in between, our code will be powerful enough to reconstruct this, to get it correctly. And this is the idea of puncturing. We know we have powerful codes. We don't even have to transmit all the bits, because our decoder will take care of it. It will reconstruct the missing bits. So this is what is done here. Just for the encoded bits, only every second is transmitted. So this is why we get the rate 1/2 here. The constraint length is 5 for this example. So we have a memory of 4. We have also the generators provided here. So they use the 37 and 21 generator. It's basically all branches for the feedback and just the first and the last for the feed forward. They use the 256 by 256 block interleaver, exactly as we have drawn it, just bigger. And the block length of this 65,000 bits. And here we basically see how now the performance improves from iteration to iteration. Again, as reference, this is typical. They provide the uncoded transmission. If we just do one iteration in our turbo encoder, so encoder 1 decodes, encoder 2 decodes, and then output, we will get this performance curve here. So still fairly high bit error probabilities for a given signal to noise ratio. Whereas if we start increasing the number of iterations, 2, 3, 5, 18, you see this bit error rate curves get quite steep. Code is very powerful there. It is already for 3 iterations. Let's say here we get a bit error probability of 10 to the power of -3 here at a signal to noise ratio of like 1.3 dB. So already for very weak received signals, we are able to reach really good bit error probabilities. Okay, here we have a question. So here, one student had a good remark. So the student here noticed that obviously, if we iterate our 65,000 bits 18 times through our decoder structure, this will cost some time. And actually, this is a point also if we look at decoders. For example, if we talk about latency, so how long does it take from transmitting a bit until it's decoded? So of course the latency will increase if we have more iterations. So it depends on the applications. First, if we can afford a certain latency time, we afford having 18 iterations. And the second point, also the computational complexity. Can we afford to have 18 iterations in terms of complexity, processing power? So for example, for 2 or 3 iterations, I could imagine, let's say I'm not the expert in implementing this stuff, but for 2 or 3 iterations, I can imagine we would just implement 2 or 3 stages after each other, and we could very quickly process the whole stuff. And if we have this iterative structure, I would imagine it's more effort from the implementation point of view. So here, of course, again, typical engineering task, the choice of the number of iterations would depend on your system parameters. Here, just from looking at these curves, I would say 5 is reasonable. So the improvement of having more than 5 iterations is not really so big anymore, whereas between 3 and 5, yeah, well, there's still some significant improvement. So for this set of parameters, I would say, well, let's use 5. But this will look different if you have larger constraint length, different generators, if you use different size interleavers, and so on. Okay, are there questions so far? So this is already the main story. So we still have some time left, so we want to go a bit more into detail. I use the lecture slides to show you this, because be able to in detail. So let's start here. So okay, we already talked about the encoder. Now we know why we need these 2 encoders with the interleave data to get independently encoded bits. Here we already explained the usage of variables that will appear in the equations later on. And maybe this line down here is interesting. This will at the end be the final result. So we will get the extrinsic info or the log likelihood ratio of our bit UR that we would like to estimate from getting here some a priori information. So this is the part that we would get from the other decoder. We will get some information based on the noisy observation of our bit. LC, so the C refers here to channel. So just imagine what we will also see on the equations. The higher the signal to noise ratio, so the less noise we have, of course, the more reliable will be the observation of this systematic bit. Just imagine we had no noise at all. Our systematic bit will be exactly the bit UR that was transmitted. So depending on the signal to noise ratio, this observation of the systematic bit will have more or less influence on our estimate of U. Very good signal to noise ratio, we will get a high number here. And we have this LE, the so-called extrinsic information. This will be the information that we get from decoding our bit UR using the trellis diagram. So 3 parts: a priori information from the other decoder, like channel information from observing the systematic bit, and extrinsic information from processing the trellis diagram. Those are the 3 parts at the end that will contribute So the decoder, we spoke about this already. And the decoding algorithms that we will use are different from what we know so far. So far, we have talked about the Viterbi algorithm, which basically gives us an estimate for a whole sequence. But here in Turbo Decoder, I will need estimates for individual bits, being more like a +1 or more like a -1. So we need a different decoder. We will use the so-called map decoder, and this will actually give us estimates of individual bits. This is what we will have here. Actually get an idea how this is. Again, the log likelihood ratio. So here I introduced this. We already spoke about log likelihood ratios in the context of the LDPC code. So this is not new for you. Using again this ratio of probabilities, the ln of the log likelihood ratio. Okay, and then basically just many equations here, but let me come to the diagrams which are better to explain this stuff. So just imagine one stage from the trellis diagram, and we basically see that the value of the bit being either 0, like the dashed line, or a 1 will depend on the states before and afterwards. So for example here, I just have drawn all the transitions in this trellis diagram corresponding to a 0 bit. And here we have all the transitions corresponding to a 1 bit. So note, the probability that the 0 bit occurs here is the same as the probability for certain pairs of states. So for example, I can say the probability that I get a 0 here will be the probability that we have state S0 here and state S0 here, or having state S1 here and state S2 here, or this pair of states or this pair of states. So this will be the first step, expressing probabilities for my bits, 0 or 1, in terms of probabilities for pairs of states. Yeah, well, this looks now quite difficult and we go over it fairly quickly. Here, just what I explained right away, probability for certain bit values as sum of probabilities for certain pairs of states. Okay. And then basically the whole idea of this map decoder is to process the trellis in such a way that we can estimate probabilities that certain states are reached in this trellis diagram at a certain time step. So we are looking at time step R now. We have some previous bits in this sequence here. We have some future bits in this sequence. And then basically the whole idea is to process the trellis diagram from the beginning. Imagine again, starting at the all 0 state as our registers are initialized with zeros. We can basically come up with an estimate that 0 or a 1 bit was transmitted, and by coming up with probabilities for these two events, we will also get probabilities for certain states in the trellis time. Maybe we should make an example there, so we still have some time left. So enough time to get the main idea of map decoder. main idea. Map decoder. Maximum. Posteriori. Probability. That's what the P stands for. Just start with the first part of it. So we start here at state. Label the states here from 1 or from 0. Let's mix this up a little. Start here with the 0, state 0. And for the example that we use, we could get to the state. So if we say here time step R, and we have here the actual state, S prime, the following state, and now just again to give you a rough idea, assume we transmit it let's say being a 1-bit mapped to AR being a +1, a -1, and what we receive YR, for example, now we have some noise. I mean, in the best case, we would observe a -1. If you have a small noise, maybe a -1.1 or a -0.9, or let's say we receive here a -0.8. So we had some small positive noise of 0.2. And now the dashed line corresponds to 0-bit. +1, and the solid line corresponds to a 1-bit being mapped to -1. So this value YR, this is what I get directly from my systematic bit. I can observe this at the receiver. And for example, if I observe this -0.8, considering additive white Gaussian noise, small noise amplitudes are more likely as large noise amplitudes. So if I observe a -0.8, then more likely the -1 was transmitted as if the +1 was transmitted. This means the 1-bit is more likely as the 0-bit. So the solid transition is more likely as the dashed transition. So just look at the numbers here. So maybe 90% probability. We could calculate this. 10% probability. So from the observations, of the systematic bit, we can get probabilities for certain transitions in the trellis diagram. And notice this will give us a chance to get probabilities to reach certain states in the trellis diagram. For example, we start with a 0 state, so having shift register initialized with zeros. In the first time step, we know like for 100% probability, we will start at the 0 state. So probability 1 here. So if you have the observation and the probabilities as we described here, like with 10% probability, we will reach this one. And with like 90% probability, we will reach this one. So probabilities reach certain states. And now you can imagine how the story will continue. We will do the same thing for the upcoming bit. Same thing for the next bit. So this is basically how we will go. So process, trellis, up to desired time step. So we will get probabilities for each of the states then. And we actually will do the same by processing the trellis diagram from the back, because we also need know the final state. As we use a terminated code here, we know at the end we will also have the 0 state. So in the same way, we process the trellis from the back, looking at the 0 state at the end, the noisy observation that we had before, and from this we can calculate the probability of the states before. So basically in the same way, process trellis from the back. And basically from this, we get probabilities for certain pairs of states at any point in the trellis. Which means, i.e., probabilities for certain bits. Because again, as we've seen, bit values basically are determined by the probabilities of the states. If I know probability of states before and afterwards, I also know probability bit to be a 0. I just want to show you this again on the slides. This is basically how we process the trellis. So from the beginning, we trace it to the state S. From the end, we trace it to the state S prime. And with the probabilities for these pairs of state, we estimate the bit UR. And this you will see really in many equations here explained how to do this trace back and this tracing forward in the trellis up to the point that we are interested in, and how to calculate this different matrix. So, but again, for us it's not so important now, these equations. It looks quite lengthy and difficult, but again, it's important that you understood the main idea, processing these two dependent observations basically, and how we use the trellis here basically to help us this processing by separating it past, present and future and tracing from both sides, getting the probabilities which will tell us the probability of the bit UR. Okay, there are questions related to this. This was very fast without too much math on this topic, but well, we need to set priorities, and for this year, for this semester, the priority was on the LDPC codes. Okay. See, no, one more question here. There was one question. So the student here didn't see tasks related to the Polar codes. Well, that's basically just because so far we don't really had tasks for. So it's difficult to make up tasks there because, well, calculating log likelihood ratios for such a polar decoder would just be too difficult for an exam. So also for the polar codes, I could just imagine like simple questions maybe related to the decoding, like these tables that we have, like if you know the output of the first and the output of the second, how to come up with an estimate for the input. So this is what we've done in class basically. Or then like the even more general questions, like explain the principle of channel polarization in your own words, something like this. So where you don't have to do calculations. Okay. End of
Sir, like in Hamming code, we have seen, sir, it's a single bit error correction and detection code. So, sir, in here also for decoders, it can't deal with burst errors. Like you have told the role of interleaver here. So we try to split our errors so that decoder can deal with it. So we don't have decoders which we can which is going to deal with burst errors. So
Yes.
that argument holds true here as well.
I think I got the question. So therefore, let me go back to the slides from last time. Yes, so the question was related to the burst errors. So notice, if we look at this Viterbi decoding example, if we have single errors in here, it will be easy for my Viterbi decoder to find the correct branch here in the trellis. Because just one bit different, okay, it will follow this way here. Imagine here now a burst error of like, we had 4 bits wrong here, of 4 bits being wrong in a row. For example, starting here with 1, 1, 1, 0, 1, 1. So the first 3 bits being wrong, this will give us here a matrix of 0 and a matrix of 3 here. So this path more likely. And we will have even one more wrong path. So this burst error could actually make our Viterbi algorithm fail here because just too many bits in a row are wrong. As you see, with single bits being wrong in between, my Viterbi decoder will be better able to correct these errors. So it's also a nice exercise for you. You can try to follow the same example using again 4 errors, but put the 4 errors in a row and see if the Viterbi decoder still comes up with the correct estimate. I think we can also get an idea if this will be possible if we look at the free distance. So I'm not sure what free distance we had here. Of course I can see it. So we have here 1, 1, 1. So 3, 4, 5, 6. We have a free distance of 6. So recall the block codes. For the block codes, we said we can calculate dh min minus 1/2 and the floor of it bits in a code word of length n. And here, for example, we have a sequence of length 9. The next similar sequence is different in 6 bits. So we could correct, at least as a rough estimate, we could correct 2 bits being wrong in a sequence of length 9. So I guess if you would introduce 4 errors within the first 9 bits, your Viterbi decoder will fail here. But feel free to try this out. But that's what I would say right now from just looking at it. This is then the benefit of having the interleaver. If you can make it to split up this burst error of like 4 bits in a row, like here over 3, 6, over 18 bits, then your decoder will be able to cope with it. Okay, did this answer your question?
Yes, sir. Yes, sir.
Are there more questions?
Sir, can you go back to the first slide of today's lecture?
Yes, yes. Yes, going back.
So, sir, one student today raised a question like, can we take feedback to be 0, 1, 1, 1? So, but what I think is that feedback is not possible in that case because feedback is some element which carries data from our output to input. So, in case of 0, 111, that won't be a feedback at all. Is my argument justified?
Yes, so here again, the question is about the feedback generator. So, well, of course, you could do crazy stuff, but as the codes are typically defined, it's done in this way, that the feedback enters here at the beginning of the register. Of course, you could do crazy stuff like having the feedback and feeding it back in here. Of course, you could do something like this in a structure, but what's the point then? Well, you would mix up the information in a similar way, but just it's more like consistent or more straightforward to have the feedback entering the input of your structure and not entering somewhere in between.
Yes.
It's just like a convention thing.
That won't be actually a feedback, sir, because as we have studied in control systems also, feedback is an element which carries some information from your output back to the input, right?
Yes.
So to actually lessen the error between input and output. So like I was also thinking on same line because for that particular sequence 0, 111 won't be a feedback at all because it's not getting back at the input.
Yes, yes. If you take this strict definition from automation engineering, well, then it is like this.
Yeah.
I'm not an expert in automation engineering, but just from the theoretical point of view. So, of course, you could also imagine feeding in some stuff here. Maybe you would not call it feedback then, but the purpose would be similar. You get some information from back there, again, in front of these guys. But again, convention is having it as feedback to the input of your structure.
Okay, sir. Okay. Thank you.
There are more questions. Okay, so then thank you for your attention. This was the last lecture for this semester. So I wish you guys here in Ilmenau good luck for the exam, which is still to come in March. For the students in Kazan, I noticed the results were not very good for all of them from the exam. So some really had big difficulties understanding the material. But well, of course, we are aware that this online teaching is not the best way of basically teach stuff. So I would also prefer to be in Kazan for teaching. And I think it has also shown that last year we had a week like intensive online course for the students in Kazan. And this, from my point of view, proved to be better. So the students obviously could focus more than topic. Well, for this semester, we didn't make the best experience there. Okay, so Mike Wolf is already showing up. Okay, so then that's it for today. All the best for the upcoming time and hope to see you someday in Ilmenau. Bye.